Good morning, everyone. This is just a quick note to say that this meeting will be recorded. And welcome to another seminar of this quantum series. And today our guest is Dr. Stuart Ingleby, who will present his work on advances in unshielded optically pumped alkali magnetometers. So Stuart is a Chancellor's Fellow in Physics at the University of Strathclyd, and his research in quantum magnetometers is focused on translating new magnetic sensing capabilities into real-world measurements and applications. He has led the development of digital alkali spin masers for highly precise and accurate geophysical magnetometry, with applications in resilient GNSS denied positioning, the sensing and detection of concealed objects, and the monitoring of the science of space weather. His research also encompasses ultra-sensitive shielded magnetic sensors for healthcare applications, accurate high bandwidth magnetometer for calibration and baseline correction, and tuned radio frequency magnetometry. He is a member of two national quantum hubs, both on quantum sensing, imaging, and timing, and quantum-enabled position navigation and timing. Now we'll just shut up and ask Stuart to step in. And if you have any questions, please use the question and answer tab on the top of the Teams call. Stuart?
Great. Thank you very much, Aurora. Good morning, everybody. Thank you, Aurora and Barrett, for the organising this great seminar series, and I'm really excited to be able to speak to such a wide range of people this morning. So it's great to do this. I'll just share my slides, so hopefully we don't have any technical problems there. How's that? Good, excellent, thank you. So yes, exactly. I've been working on these unshielded optically pumped magnetometers for a little over a decade now, and what I'm going to try and do this morning is walk you through a bit of a story that covers quite a lot of interesting physics, interesting measurements, and so this is why I start with this slide. It's got lots of pictures of happy physicists doing physics in exciting places with exciting technologies, and underpinned in all of that is this story that why bother with unshielded optically pumped magnetometers. So I'll talk a little bit about what motivates that, where the key applications are. Then what does that mean in terms of the underpinning physics that you really need to have a handle on to have useful optically pumped magnetometers in unshielded environments? Where did that lead us in terms of our development? That's a nice time to digress and talk about some of the field measurements that we've been doing increasingly over the last few years. I'll then dive back into the detail of the physics a little bit more. How do you refine these sensors? What's important for getting to the next stages in precision and accuracy with them? And on that note of accuracy in magnetometers, which I think is a really important performance metric, how do we achieve that, and then what can we do with that? And I'll finish the talk off with a bit of discussion on that. So, starting off with, this is many of you will have seen this already. This is my one slide overview of how an optically pumped magnetometer works. This is the simplest one that you can build, and compared to a lot of very complex experiments in quantum technologies and photonics, what we need optically is quite modest. We exploit the fact that we have resonant interactions in alkali atoms that can be driven simultaneously on the optical transitions and the magnetic ones. So that's kind of what's going on here. If you have this simple picture of the energy structure in an alkali atomic vapor, you have the optical transitions. This is hundreds of terahertz that link the ground states with the excited states. The excited states don't need to live very long here because all the magnetic action that we're interested in happens in the ground states. Those ground state interactions are the ones that are sensitive to magnetic fields. And what we're trying to do when we build an optically pumped magnetometer is set up a tension between the optical processes that are shifting the atoms around these ground states and the magnetic processes that print the information about the field that you're measuring back onto the atoms. So the light, in this case, simultaneously prepares the atoms, and then the back action of the atoms on the light generates the signal that you can measure. So a single laser is enough, and actually these alkali atoms, because they're very accessible optically, the laser doesn't even need to be particularly high intensity to achieve a strong signal. In fact, sub-milliwatt is enough for most of what we're doing. So we create this system that you see on the left-hand side, where we have this atomic vapor that can be a thermal vapor in a hermetically sealed cell. We have a laser, and I've deliberately drawn one in a TO can here because quite often we use a chip scale laser like a VCSEL to generate monochromatic light, and that light is preparing the atoms. They're undergoing back action from the magnetic field, and then we detect the influence on the light from that back action. And what that typically looks like is magnetic resonances. And for cesium vapor, in this example, the Earth's field magnetic resonance in cesium vapor is about 175 kilohertz, or at least it is in this part of the world. It varies by about 30–40% from that figure. So it's all geomagnetic measurements with cesium atoms don't leave you with a difficult modulation frequency to generate and measure. This is all things that can be done with very high SNR with scalable electronics, and you can tune this sensor up in a variety of ways. You can measure that resonance frequency to determine what the DC magnetic field is, or we can tune the DC magnetic field and gain access to a very interesting frequency range, SLF, ULF, VLF frequency bands, or if we choose to, we can put this whole sensor inside a magnetic shield and detect very accurately where we reach a zero field. The interesting thing that happens there is that these magnetic resonances that I've drawn on the right-hand side there become degenerate when you reach zero, and you get another very sharp resonance feature, again, that can be observed with a single laser. And that's the basis of a lot of biomagnetic sensing. I'm going to concentrate on geomagnetic measurements in this talk, but the principles are the same across all three of these really interesting measurement modes. And like I was saying, the way that the laser is small, the frequency range is benign, it means that you can build sensitive and high SNR packages, 90+ decibels, in pocket-sized magnetometer packages. And that leads the way to doing lots of exciting work in developing applications for these sensors. So if you have to take one picture away from this talk, I think this is the one that I would summarize with. So to motivate a little bit of why is this work worthwhile, I like to think about the mapping of an application space, what things are needed to do what tasks, onto a technology space, which technologies give you access to those properties. And the three properties, the three metrics that I would suggest judging against it are these circles on the Venn diagram. So we've got femtotesla sensitivity, which you would need if you want to do biomedical measurements, but also if you want to detect hidden objects. Submarines, ordnance are quite hot topics, unfortunately. Critical national infrastructure protection, you also want high sensitivity for that, but that also combines high sensitivity with parts per million accuracy. There's no point in having for critical national infrastructure protection, we're typically looking to do things like measure space weather over extended periods of time. And being able to measure in the femtotesla is important, but it's also important to be able to measure with parts per million accuracy. And that's just as demanding a precision measurement as that sort of short, very low noise measurement. So that's why I bring it in as another sort of performance metric. Geomagnetic observation also falls into that. If you want to navigate with respect to the Earth's magnetic field in the absence of GPS, then you also need high accuracy. And sensors that you're going to put out in space for long periods of time also need to be very accurate, intrinsically accurate. The third aspect there is we need sensors that are low swap. And by low swap, I mean something that it can be handheld, can be powered from things that you can carry. I think that's a good metric. A person is a good vehicle for carrying a magnetometer. So is say a CubeSat or a small UAV. And in all of those cases, you can't really tolerate more than a few watts and a kilogram or two. So that's the application space. And then the technologies that might help you fill those applications for high sensitivity, cryogenic squid sensors, excellent. Femtotesla magnetometry with those very successfully demonstrated. But they certainly don't, they're a relative sensor, and they certainly aren't scalable. You need a joule of liquid helium typically to run those in. Part per million accuracy, the gold standard there is a proton magnetometer, but that has a very low cadence. It's not a sensitive device, and it's actually quite bulky and heavy to carry because it relies on NMR rather than alkali magnetic resonance. Low swap handheld sensors, there are lots of these around. Fluxgate magnetometers have been around for 80 years. They're certainly low swap, but they don't have the accuracy and sensitivity. OPMs give you a chance to develop a sensor with all three of those, and I'll demonstrate the kind of things that we do to achieve that. So that's why I'm interested in OPMs. They do sit at a really nice intersection of capabilities. And the simplest OPM that we can build, we can take that picture of the atomic structure and say, well, I'm just going to pump all of my atoms by exciting them to the ground state, letting them fall into the exciting them to the excited state, letting them fall to the ground state. In the process of doing that, the angular momentum from the laser gets transferred to the atoms, and I can push all of those atoms into an oriented polarized state like this, and then anything the magnetic resonances do to pull them out of that state can be measured. So one of the best ways of doing that is to drive, in the presence of a static field B0, to drive those atoms with a resonant radio frequency field that tips their magnetization away from this optical equilibrium and then into a dynamic state that evolves with a magnetic field that has a back action on the light that we detect. And typically what we see is a sinusoidal resonant signal. The interesting thing there is that the phase information also tells you about the magnetic field. So this driven oscillator system with its amplitude and phase information that you get out of it gives you a very sensitive magnetometer. However, although the sensor here is very simple, there are complicated effects to do with the geometry of the magnetic fields, what happens when we have more complex unresolved optical spectra that govern the design of that sensor for practical applications. And the geometry of getting these static and radio frequency fields in the right orientation was something that a decade ago, we dived into the lab and we realized we had to do some preparatory work there before we could build these compact sensors for using in the field. So this geometry question prints some really interesting information onto the amplitude and phase of the resonance signal that you get back, particularly the phase. And there's some quite useful bits of underpinning physics that allow you to understand that in detail. As I was saying, the atomic structure that we deal with in cesium is a lot more complicated than the simple picture on those first two slides. Rather than the 6 levels that I showed you, there are 2 manifolds, each of which has 16 levels. So there's a 32 level system that you need to be able to understand. And a very effective way of doing that was to do a multiple expansion of the ground state. So this is an equation that I'm just going to throw out there. Maybe doesn't mean a lot to many people, but the density matrix is the sort of typical atomic physics way of describing those ground state behaviors. We could get somewhere by expanding that density matrix in terms of spherical harmonic tensors. And by doing that, we convert our polarization into moments multiple moments for the atomic ground state, and we can convert those into signal moments. So we can relate the pumping process and the driving process to geometrically transformable multiple moments. And by doing that, we can perform those rotations of the static field and RF field in theory, as well as we can do them in the lab. And this is what we did. So this is the phase of that atomic resonance signal as we tip the direction of the field that we measure around a full sphere, all 4 pi solid angle. And you see that there's a very strong dependence of signal phase on the orientation of the static field. So this is a really important bit of enabling work, because what it allowed us to do is understand that phase change in the system is not a systematic error that we have to fight against, but actually it's something that gives us information about the direction of the magnetic field. And the data that we took in the lab with our lab model magnetometer really nicely matched the model that we had from theory. So we kept going with that, and we realized a completely unexpected benefit. Again, we have more of these theory plots in the corner and more of the lab data. And you see, in every case, the theory matches the lab data. And what we were able to do with a very simple magnetometer, we could pull out phase and amplitude information at the first and second harmonics of our modulation field, and use that to actually derive what the angle of the static field that we were measuring is. So this is a way of turning a scalar magnetometer into a vector, but also what it gave us was a really strong handle on phase-induced systematics in a scalar measurement with an arbitrary field orientation. And it was an important enabling step that allowed us to start designing RF-driven magnetometers to put out in the field. And this was the sort of crowning achievement of that vector measurement. We could swing our magnetic field all around inside the lab, and the sensor would resolve those angular changes because we had models that were predictive of the phases of the harmonics in the signal. However, there was another bit of underpinning physics that was problematic for us that we wanted to understand in detail first. And this is the idea that if we take the solutions to the dynamics of that spin polarization, we can solve those in the presence of a static field that doesn't stay still. So here we introduce a frequency. This is omega, small omega s there. It's the signal frequency. What does our sensor do when we want to resolve a signal that isn't static? And in practical terms, every signal out in the real world is not static. Whether it's the one you're interested in, say a heartbeat or space weather, that has a frequency characteristic. It's existing in a world full of noisy things that have their own frequency characteristics. So if we want to build a magnetometer that can resolve signals of interest in the presence of noise that may be even higher than the signal magnitude, we need to have something that has bandwidth and linear response with changing frequency. So we need to understand these spin dynamics. And this is an expression here for the oscillating signal. So you have this e to the I omega signal there. This expression for the oscillating signal that we observe under changes in the magnetic field is interesting, because what it tells us is that there is a bandwidth limitation depending on the relaxation rate, that's gamma 2 of the atoms. So here's your sort of simple picture of what the atoms do under the influence of a magnetic field B0. They relax to equilibrium, and the RF field drives them and prevents that from happening. But usually for a sensitive magnetometer, you want gamma to be small, so that you have a very nice long-lived magnetic resonance that you could only need to drive weakly to make it ring. However, this is showing you that if gamma is small, then at fairly modest omega s, your signal gets killed by this term out the front here, and its phase is distorted, because this is all complex impedance, if you like, on the signal. So that's a big problem. So even in the presence of, well, without feedback, we have amplitude loss and phase shift in our signal, which is going to limit our sensitivity and distort the signal and the noise together. And even with feedback, rotations of B naught can result in transient phases because of things like Berry phases, for example. So the dynamics of this system are critically dependent on the feedback that we apply. So we wanted to develop a rapid and linear method for applying feedback, tuning this RF field to what frequency is required in the Earth's field. So we went from this PID sort of model for feedback, this block diagram, to one where feedback is not a question of frequency going around the loop, but phase. Our detector sees a phase from the atoms, we make a transformation on it, feed that phase back in, the atoms are ringing, they are resonating in the magnetic field, no matter how rapidly the magnetic field slews to different values. The other nice thing about measuring phase in this way is we developed a way of determining frequency very rapidly. So this is a magnetometer that has very linear and uniform response, but also very rapid response to changes in the field. And that all depends on the design of that filter. Possibly I shouldn't dwell too long on this, but we needed a filter with a very uniform phase behavior and a very flat frequency behavior. And we developed a method for the design of that filter, which enabled us to publish this new method for running a magnetometer. And as it's a digital feedback loop, we can switch it on and off as we like. This is just an enable pin on our FPGA. So in the absence of feedback, you get this atomic signal, very small in amplitude. This is basically thermal and technical noise that you're measuring on your polarimeter. We switch the feedback loop on here, and then the atoms just start generating their own frequency. This is in the Earth's magnetic field. This is actually data I took on my desk at home during lockdown. We close the loop on the FPGA, the atoms start resonating. We have a persistent resonant frequency. It very quickly builds up to a nice amplitude. And then we ask ourselves, how accurately can we find the value of the magnetic field generating that frequency? So when we look at the spectrum of that resonant signal, we have a frequency that we're trying to measure, the Kramer-Rao lower bound, which is the mathematical limit on how well a frequency can be determined from a given signal with a signal to noise. So that's A over rho is the signal to noise ratio. Tau is the time that you measure this frequency for. With our initial system, we had a signal to noise ratio of about 3000, which you see there. And in 1 second, that would give us 50 femtotesla magnetic resolution. So here we have something which is operating in a small optical package, giving us part per billion magnetic sensitivity. And it's all because our system is really resonantly driving. We're enhancing our SNR through optimizing that feedback loop with the FPGA. So now we have a lot of the tools here to start putting sensors in the field. We have a scalable bit of electronics, a small sensor head with a single laser and a scalable cell inside. Everything can be moved towards a fieldable system. And this is a nice picture that my colleague Courtney Dyer has produced of what that actually looks like in practice. We have a microfabricated cell inside there containing the cesium atoms. The RF field is applied through a coil and a heater on the back there. There's a dielectric mirror. Static field wants to be oriented in a direction that gives us a good signal amplitude. And there's a single laser source there that is retroreflected through the cell onto a polarimeter. The whole thing fits into a package which is definitely pocket-sized. This is something that we can now take out in the field. And these are the sort of essential characteristics here. The relaxation time in this cell is something that we've optimized. I'll show you later how we do that. We have about 1/350 hertz coherence time. So that shows you that even in quite modest systems, those ground states can have nice long-lived magnetic resonances. And this is the real workhorse of a lot of the application development that we've been doing since then. So now I will move on and show you some of the interesting stuff that we can do to explore and to characterize how this sensor works in applications. One of the projects that we started a couple of years ago was to do this at 5 new field locations for geomagnetic sensing. So the British Geological Survey have the UK's geomagnetic reference magnetometer that sits at Estailmuir Observatory, which is, don't know if you can see my cursor, but there's a blue dot in the Scottish borders there. That is the UK's geomagnetic observatory. In fact, it was the first in the world to be purpose-built as a geomagnetic observatory. Monitoring space weather is scientifically very interesting, tells us a lot about the Earth, the ionosphere, the sun. It's also economically important because large solar storms happen once in a while and can have very serious impacts on transport, communication, and power networks. Which I only have time to scratch the surface of some of those, but there are actually papers out there that show a few volts on the railway signalling network is enough to turn red signals into green ones. And the railway signalling network is a pretty good antenna for space weather. So as well as this being a scientifically interesting study for the British Geological Survey, there's also important critical national infrastructure aspects to this. And to study space weather well, you need a distributed network of sensors, which is what the figure on the right shows here. Our task here is to build 5 new nodes to fill in some of the gaps and give the UK the highest density distributed network of space weather sensors in Europe. And that's exactly what we have been doing in collaboration with BGS and RAL Space. We've been installing sensors of the type I just showed you at these 5 new locations here to increase the density of our resolution of space weather. So, yes, a nice picture here of the Estailmuir Observatory. This was, like I was saying, it's the BGS were among the forerunners of measuring space weather. There's some wonderful data from the 19th century showing some of the very first observations of the magnetic impacts of solar storms. But the BGS, around about the turn of the century, as the electric rail network moved towards their headquarters in Kew, they realized that they had to measure geomagnetic signals somewhere much quieter. And they went just about as far as you can get from the rail network to Estailmuir, which is a wonderful place to do geomagnetic measurements. What this observatory has is a bunker and a number of huts around there. The bunker contains 2 exquisitely well-engineered classical variometers, the best flux gates that you can buy. But they are not accurate enough over long periods of time. In order to get that reference measurement for measurements of space weather, protection of national infrastructure, those flux gate measurements that are taken in this thermally controlled bunker need to be disciplined by a number of proton precession magnetometers around the site. So a geomagnetic observatory is a suite of instruments that produces a reference. The idea of the OPM is combining precision and accuracy. We can replace a suite of instruments in a compact package, and that's what makes the OPMs attractive for field installations. We can't afford to build another 5 of these observatories around the UK. We want to have a single sensor that replicates the performance of those that can be distributed and run in a low power distributed way. So that's our aim with this project. This is the example of when we take our sensors to Estailmuir for validation. The orange traces what we measure. On one part of the site, it's been offset for clarity from the observatory reference there, but you see that we map changes in the magnetic field very nicely there. And this is a really useful measurement of solar geomagnetic activity and its impacts on Earth. And getting this long-term agreement in the data is what gives us the confidence to go and install those field sites. So I have some data from a pilot study that we did in 2023. This was excellent because we got ourselves in the media, the Oban Times, which is one of a long-established and excellent reputation local newspaper. The article, I think, compares the cost of this experiment to the Large Hadron Collider, and I think we came out very favourably. The OPM is sitting in a little weatherproof box here, and we run it off this solar panel. And by doing that, we could measure the spatial distribution of space weather events. So here we have the British Geological Survey's reference data from Lerwick, from Eskdalemuir, the purple one, and from Florence Court, which is in Northern Ireland. So Lerwick is in Shetland, it's the far north. So these roughly go north to south, and you can see that the effects of geomagnetic solar activity are more pronounced closer to the North Pole. We had data from South Uist and Isla at the same time, and we can see the spatial distribution of solar storm magnetic events in this data. So that's ongoing work, and I hope that one day we'll be able to show you not just two quantum magnetometers, but 5 traces there, really building up a spatial picture. The next sort of case study I was wanting to show you is our results on geology. So here we take our sensor and put it in a wearable system. There's some pictures of that on the next slide or two, I think. But this is something where we can walk about 30 kilometers, and we did this in collaboration with a real interdisciplinary team from Aberdeen, Edinburgh and Durham University of proper hardcore geologists who taught us an awful lot about surveying techniques, the state of the art in their instrumentation, which they brought along: proton precession magnetometers, gravimeters such as Syntrex CG6, and we use that alongside long-term seismograph data from buried seismometers. We're really interested in the Highland boundary fault. Do we understand its structure? So this is really where the Highlands meets the lowlands in Scotland. It's where the mountains start. You can see the central belt here is all flat and the Highlands is all mountainous, and that comes down to the geology. The Highland boundary fault is where these plates have come together, and the structure is somewhat understood, but the region around Blairgowrie is very interesting. So we resurveyed that in detail. And this was very interesting for us because it really showed us what we can add in value to a geomagnetic survey. A proton precession magnetometer is a very, very accurate device because there's a nuclear spin that it relies upon. The nuclear spin, unlike cesium that has those 32 levels I was talking about, nuclear spin of a proton has 2 levels. It's either up or down. So lots of systematic effects to do with geometry are not present in the proton precession magnetometer. It's a very accurate device, but very slow. So the proton precession points over our 20-kilometer baseline here are these single dots, and we have some zoomed in regions here. Along that whole track, we also have OPM data, which is the blue continuous line. The OPM really speeded up the survey process, but also it allows us to discriminate magnetic clutter, so man-made magnetic fields, from the geology that we're really interested in. So in general, you can see a very strong magnetic signature due to the fault line in the middle here. But this is not an area of complete wilderness. Actually, a lot of the survey was around farms and towns and man-made magnetic field sources. So an example of that is in this region here around A, that there are some man-made magnetic field sources here. This could be just a fence line, for example, but that causes a bump in the proton precession magnetometer at 1 that you can't really tell the difference between that and the other bump that the PPM sees at 2. But the OPM does. The OPM resolves all of this fence line structure and magnetic stuff here, the spikes, and it allows us to pick out this broader trend which underpins the data at 2. So actually it turns out that this is a narrow dike, so an igneous formation of rock with a narrow spatial extent that we walked over, and with the OPM data in combination with the PPM data, we could discriminate it from this man-made magnetic noise in other places. There's some other examples of that from other parts of the survey, places where our OPM data allows us to sort of triage this spike in the PPM data. This is probably man-made. We can see passing cars, for example. So you're seeing the value of precision and accuracy rather than just accuracy, that precision and accuracy gives you the ability to work out what you're looking at. So this is exciting work, and I hope we'll be able to take it further. But precision and accuracy is what we're aiming for, and accuracy with an OPM requires a little bit more of an in-depth dive into the physics. So I presented previously a very simple picture and told you that we had this neat mathematical trick with the multiple moments for simplifying it. This is what the complicated picture looks like, at least for cesium atoms. There's a similar one for rubidium. We have these excited states here that we are optically pumping from the ground states. That's this green process, typically going on at rates of about 10 million times a second. An atom gets thrown from the ground state to the excited state at sort of tens of megahertz. But to achieve narrow ground state magnetic resonances, we put buffer gas into our cells in order to slow the diffusion of our alkali atoms to the walls. And the presence of that buffer gas means that the lifetime of these excited states can be 1/gigahertz. So much, much faster than the atoms are being put up there, they're coming back down again through a variety of interactions. And it means that these excited states are not well resolved in our magnetometer. We need to understand the processes that are happening in the presence of that buffer gas, which is the sort of relaxation and decay back to the ground states. And quenching on nitrogen molecules is a really important part of that. Those are all, from the point of view of preserving angular momentum in the ground states, those are quite benign processes, but there's still interesting physics that we have to resolve there. Then we have ground state processes that do destroy our spin coherence. The Zeeman resonances that we're wanting to measure are typically hundreds of kilohertz, but included in there that would be impossible to see on a diagram like this. There are nonlinear Zeeman resonances at tens of hertz, and there is the hyperfine difference. So that these two ground states here have marginally different gyromagnetic ratios, which result in interesting systematic shifts that are mediated by the population balance in these states. So we need detailed models of the physics in this very sort of jumbled system to allow us to optimize and understand our systematic effects. We have some confounding processes like spin destruction, thermalization. That can happen at tens of hertz. It's all to do with how the atoms collide with the walls, each other, the buffer gas. And there's also spin exchange dephasing that can be very significant and is an effect that you need to suppress in order to achieve high sensitivity. And this is happening because an atom in a state that we might want to measure, say 1 in F equals 4 over MF equals 4 in this stretched state here, may collide with a stray atom that's left in F equals 3. They process in opposite directions, and then after subsequent collisions, that angular momentum has been lost. It's become incoherent because of that opposite precession frequency in those two ground states. So there's a lot to take in here, and it's not the right forum to teach an undergraduate course on this. But the point I'd like you to take away is that it's a complicated picture that we have to understand in detail in order to optimize our sensor, and doing things like suppressing spin exchange dephasing is critical. So the way that we do that suppression of spin exchange dephasing is by changing our optical pumping scheme so that we not only pump the atoms in the F equals 4 manifold that we're interested in, but we very heavily pump the atoms out of F equals 3. This is a process called light narrowing, because the effect that it has is to take that spin exchange dephasing and make it much, much less likely to happen. It all relies on collisions of atoms between the two ground states. If you've engineered the atoms to sit in one of the ground states, then you've effectively suppressed that very significant impact on your ground state magnetic resonance, and in doing so increased the contrast and the resolution of the magnetic measurement that you make. So this is a process called hyperfine repumping, and it's a way of achieving those femtotesla sensitivities even in the presence of non-zero magnetic fields. It also has a beneficial effect on hyperfine systematic shifts, because again you're suppressing a population of atoms that sees a slightly different gyromagnetic ratio. So when I was talking about the proton precession magnetometer, how it has two states that you have to care about, this is our way of simplifying lots of states out of the picture if we can suppress the population in one of these. And this is a really important work that was one of the first practical demonstrations of this. So key to this is designing a cell in which we can do this process. And this is something that we've had going at Strathclyd for a long time. When I talk about a cell, what I mean is an anodically bonded chamber that contains the cesium and the gas content that we need. And we've manufactured cells with a wide range of geometries and compositions. We can tailor them differently for magnetometry, metrology, and for timekeeping. And it's a really important enabling step in making these magnetometers more sensitive and more accurate. So here's an example of what we can do. We can fill a cell and we can keep our alkali source off to the side if we want in a little chamber like this. So this is work that James Gilligan and his team have perfected over a number of years here at Strathclyd. So then when we measure that alkali source by absorption measurement in the science chamber, we can obtain something like this. Our cell has this black spectrum, absorption spectrum, a reference cell that would have no buffer gas as this blue one. And after we've activated, we have about 150 torr of nitrogen, which is a good place for doing magnetometry. We can then continue activating that pill, and we can start to regulate the amount of nitrogen in the cell, which this video shows. This is a time lapse that shows a continuous stepwise activation of that cell. And as we do so, the nitrogen content is tuned and the magnetometer cell becomes more like the reference cell. We keep this process going and we can really get down to the fractions of a torr. So now our magnetometer cell has become a reference cell. And this is not only something that allows us to tune magnetometer cells for optimum performance, but also build optical references using these same cells. And it's a really elegant combination of physics and engineering to manufacture these. How do we know that we have an optimized performance? Well, our models of the alkali ground states allow us to estimate our relaxation rates. And when we can do that by measuring magnetic precession frequency in those cells, and by doing that at different gas pressures. So as we go through that video, our magnetic resonance line width rides down this green curve according to theory, where it has a contribution from wall collisions and a contribution from gas collisions. When those are balanced against each other at the bottom here, we're really optimizing our magnetic resonance contrast, which goes inversely with the relaxation. So when we get down to 150 hertz, we have some of the most magnetically clean and optimized cells in the world that are available. And these are mass produced, which is almost a unique capability. So this underpins the development of better sensors here. And this is the other half of the better sensor. So here we have a scheme for far more accurate magnetometry. We have an alternating pump probe setup. So we take our cell, this is a laboratory test inside a shield, and instead of driving it at the same time as we're probing it, we drive it sequentially. So we heavily polarize the atoms, then we measure the Larmor frequency with light off resonance probing, which reduces light shift heading errors. And it's critically dependent on how well we can optically pump the atoms. And there are a few strategies for doing this. Some of them don't scale well. Some of them require active optical modulation at high frequencies. We have developed one that is far more scalable, and that is where we apply, using a heating coil, a very strong polarizing field. So here's the heating coil around our cell here. We can apply some milliteslas of polarizing field that is well aligned with the optical pumping, gives us a very high polarization, very high suppression of spin exchange, and we can switch our polarizing field off in fractions of a microsecond, which is useful because it allows us to do a very clean magnetic measurement afterwards. So you see we have a long-lived alkali polarization with an optimized cell and a short-lived pumping pulse that gets us to a very high spin lifetime. Then when we measure that frequency, we have simultaneously very high precision, so 240 femtotesla per root hertz, but also very high accuracy. When we benchmark that against the reference at the Estelle Muir So the SDMUR reference again is the orange one here. Strathclyde magnetometer is the green one. You can't tell the difference between those traces by eye. The offset here is artificial, so you can see the difference between them. What we do instead is we look at that differential signal. So here's delta B between our two measurements. And you see this data set here is not a few seconds, it's tens of thousands of seconds. This is a whole weekend of data. When we take the Allen deviation of that over the whole trace, we're never deviating by more than a couple of hundred picotesla from the observatory reference. For periods of time up to 3 hours, we're actually sub 100 picotesla. So this is, in accuracy terms, this is a game changer. To have that stability and scale factor as well as that high sensitivity is a very exciting capability. So for space weather, I think it has obvious applications, but one that's now open to us is navigation with reference to this signal. So this is the next sort of field measurement that we've done. Because we have a sensor that's now accurate and drift-free and high precision, we can do things like walk over the naturally occurring anomalies in the Earth's magnetic field. So all over the UK and all over the world, volcanic activity has locked a permanent crustal field that is quite a rich and interesting crustal field into the geology of the rocks of the Earth. So it's a reference that should give us some useful navigation data, but we need to be able to carry a magnetometer that is accurate enough to do that. So this next generation free induction OPM allowed us to start work on this navigation technique. We have to do, this is my colleague Sterling Scholes here, who's done a lot of work on how to actually carry one of these and get that high accuracy measurement. It's impossible to completely demagnetize all of the electronics, but he's developed ways of eliminating that hard iron error from the data. And what we end up with is an accurate map that we can build with the OPM. We turn that into an interpolated magnetic anomaly field, and then we can subsequently navigate over that area that we've mapped on quite a complicated path. And as we do so, the measurement of the magnetic field that we make is an excellent agreement. So the measurement is the blue one, the map, the interpolated map is the red one. And in order to get that interpolated measurement, we need to use our differential GPS that provides the navigation ground truth for this measurement. But what the OPM is now giving us is excellent agreement over an extended period of time where we've moved over a magnetic landscape, and now we're able to infer our position from that. And that's exactly the work that we're doing. So this is still less than 3 months ago. We're working out how to build that analysis model that gives us the navigation result from this. But it looks very promising. A lot of bits of technology are falling into place here to demonstrate a completely new and independent from GPS navigation modality. So I think that's been a very rapid tour of some of the things that we've done with geomagnetic optically pumped magnetometers. There's a few things that hopefully you take away from this. One is that everything we're doing is underpinned by cutting edge microfabrication techniques that allow us to mass produce sensors that are optimized. We rely on methods for very efficient optical pumping that is underpinned by all that detailed physics that we still do in the lab. In-loop digital feedback and signal processing is essential here, but the alkali magnetometers are well tuned for that because they give you frequencies that you can handle easily in the digital domain. And all of this allows us to do accurate, precise and portable geomagnetic measurements for a range of exciting applications. So I should briefly acknowledge the principal funding bodies and collaborators in this work that are at the bottom of the slide there. And I'd like to finish by acknowledging all the people, this extended team of people who have all contributed so much to the work that we've done at Strathclyd. So thank you very much for your attention this afternoon.
Thank you so much, Stuart. That was absolutely fantastic. Thank you. So if anyone has any question, please feel free to write on the question and answer section or in the chat, whatever suits you the most. And while people populate the section, I would like to ask a couple of questions actually. So in the beginning of your presentation, you mentioned quite a few aspects of the underpinning research. So it seems that you had to overcome several challenges. So what was the most difficult challenge to overcome to move from the lab to the field?
Yeah, that's a good question. I think that the getting the electronics to scale is difficult, because simply speaking from personal experience, what we do as physicists, we know the experiment we want to do, and then we build up a lab setup from modular and flexible bits of equipment. So we might have a DAC card with loads of channels on it, loads of bandwidth, but something that's quite bulky and doesn't really scale well. Probably it also has a proprietary programming environment, and also those are just terrible for putting in field systems. So breaking out of that flexible general purpose electronics environment into something that is specific purpose and scalable is really difficult, and it's something that we still have to do a lot of work on to push that forward.
Yeah, well, I came to realization that academics has a very different concept of portable with respect to industry, for example. So we do have a question here. When modeling the system, how many energy levels can you normally simplify out? How long do the calculations take to run? Yeah,
again, that comes back to quite an interesting point, that yes, you could sort of number crunch your way out of that. You could take, in cesium, you could take, say, 32 levels and build a density matrix for those and numerically integrate that to get some steady state solutions. And that would take you a long time. What we did was a bit different. We came up with this mathematical expansion that allowed us to express just the symmetries of the density matrix. And then we could do things much more quickly, just analytically almost, because if you can, instead of taking the whole picture, you pull out, here's the population, which doesn't have anything interesting particularly happening with it, but then here is the orientation moment, so the vector moment that comes out of that population, and we can isolate that because we've expanded into just that order of spherical harmonic. We can isolate that and analyze its behavior. We can solve an analytical model for that, or we can take the next moment up, which gives you a different harmonic in the signal, and we can analyze that analytically. So we've not relied too much on number crunching, and we've relied a lot more on being able to pull apart the different moments of the atomic system in the ground state and analyze them analytically in isolation. And we're helped by that, by just that old classical physics nugget that a magnetic field and a rotation are effectively the same thing. So if you can find a system where you can do geometrical transformations, you can model magnetic interactions quite nicely with it.
That's great, thank you. And I've seen in one of your latest slides that for the field trials you have done in December, you're still analyzing the data. So I was wondering, how long does it take to analyze the data typically?
We have an initial result. So again, that's not, the data that we're analyzing is around about an hour's worth of navigation path, and you can analyze that. Our approach initially has been using a particle filter, and the analysis on the particle filter, we run it on a laptop. You could maybe have something more powerful, but that can be done in a few minutes. It's not a particularly time-consuming analysis method. One of the interesting things is it's not the only analysis method. I think that once we're happy with that sort of bread and butter analysis, the door is open to trying lots of more interesting things that might allow us to extract more from the data.
Okay, thank you. So another question is for the space weather sensing, how much of a warning do the ground-based magnetometer readings give in event of a solar storm?
They allow you to quantify its magnitude in real time. So I'm gonna hedge my bets there and say that this isn't an early warning system, but what it can tell you is it can give you an accurate threshold. It's a much better way of assessing the severity of a solar storm than watching the aurora, for example. There are very interesting techniques for, it's another type of alkali optical spectroscopy that underpins standoff measurements of the magnetic field in the sun's plasma that are being carried out and developed at Durham University that would give you that early warning of a solar ejection coming in the direction of the Earth. So that would be, I'd say that's the best bet for early warnings of solar storms. Our role here is more about understanding what they do when they arrive at the Earth and quantifying that properly.
Okay, thank you. Another question, can you please tell how much sensitivity of magnetometer in an unshielded environment in terms of picotesla over square hertz?
So the free induction magnetometer has a noise floor of about 200 femtotesla per root hertz, and that's all the measurements that I've showed you are in. So there we are, 240 femtotesla per root hertz. And all the measurements that are in this talk are carried out in 50 microtesla fields. The sensitivity of the magnetometer is the same whether we measure it in a shield or outside the shield.
Okay, and same person is asking, is the MEMS cell is a pill-based?
That's right. There's a variety here. So the tuning is pill-based. So for the cells where we want to have very precise control over the gas content, those are based on a size getter pill. Several of the other cells that we've used have been filled using alkali azides, and we're equally comfortable with both techniques. The pill-based method is quite attractive from the scalability point of view because it's also a far safer process to do in engineering terms than the handling alkali azides, which are kind of dangerous chemicals to handle.
On a different aspect, would you be able to comment on areas of relative UK strength with this technology?
Yes, and I think I'd immediately go to microfabrication of critical components. I think that's something where increasingly people from around the world who are interested in high performance magnetometers are wanting to work with us to develop those enabling components. We have very exciting discussions and collaboration with researchers who are building satellites to go into deep space. The quality of the enabling components that we've got developed in the UK and particularly at Strathclyd is something that has a worldwide visibility. The other aspect that's maybe less tangible, the UK has quite a good ecosystem for linking end users with technology development. You know, all this work that I've showed in these slides here, it's all built in collaboration with people like the British Geological Survey, other government agencies, RAL Space, just as a few examples. Those collaborations enable you to go and do enable you to go and do that sort of application development with them, and being able to make those connections is something the quantum technologies programs sort of catalyzed in the UK. It's created interest amongst end users and allowed you to create the connections that you need. We've derived an enormous benefit from working with BGS at Estelmuir. And so that whole ecosystem is what's established that connection.
Okay, thank you. How did you manage with the transverse components of the magnetic field? Were they problematic at any point?
So, I mean, I sort of interpret this to mean the components perpendicular to the one that we measured, or maybe. So I don't know if I misinterpret the question, I'm happy to take another go at it. But fundamentally, the sensors that I've showed here, apart from the sort of phase trick at the start, were designed as scalar magnetometers. So we have this double resonance scalar magnetometer and this free induction scalar magnetometer, and they measure the length of the magnetic field vector, kind of to first order insensitive to what direction it's in. So there is a lot of information there. If the variation in orientation of the field is important for the measurement you're trying to make, then you would design a different system. For measurements of the magnitude of space weather, measurements of GPS denied navigation, it's actually quite helpful to factor the change in orientation out of the data, because it gives us something that's much more like the baseline measurement from a proton precession magnetometer.
That's great, thanks. I see a couple of questions that ended up in a comment. So in case of a GPS denied navigation using magnetometers, what's your comment and critical part of the system? And also, do you need any model of the carrier to cancel the ambient? If so, how critical is it, or computation resource requirement in real time?
So the first part of the question, I think, was on where the critical parts of that system are.
Mm-hmm.
And the thing works at the moment. I think we have the minimum viable GPS denied navigation tool that combines a quantum magnetometer, a classical magnetometer, a MEMS I'm looking for accelerometer and gyroscope, and the ground truth is separate to that. So that's the minimum part of the system. You need a stable scalar, a good vector that allows you to back out hard ion effects from your platform moving, and you need some kind of accelerometer to compare to that. Without any one of those parts, you can't really get to a navigation solution, because you need to do that hard ion suppression. So it's not that there's one critical part. If you miss any one of those, if you take just the classical magnetometer and the MEMS IMU, you don't get a navigation solution that's as good as the one that you get with the OPM. So it's all three of those together, and it's the combination that's critical. I think you could elaborate on it if you wanted to, but you do need to have all parts of the system working in tandem.
Yeah.
And this, remind me again what the follow-up question was.
1 second, incoming. Do you need any model of the carrier to cancel the ambient? If so, how critical is it, or computation resource requirement in real time?
So I'm not quite sure. Is this carrier as in the platform that you carry, or carrier as in the background magnetic field?
We'll see. Let's see if Aishik, if you could clarify your question, please. In the meantime, on these slides, what causes the noise from 10 to 50 hertz?
So the 10 to 50 hertz noise in this case is the stability of the coil driver inside the magnetic shield that provides the test field.
Mm-hmm.
So we're still working on how to flatten that down. We don't see it when we operate outside the shield.
Okay. In the meantime, we had the clarification from Aishi because it's a platform.
Right. So yeah, the suppression of platform noise is something that it's taken us quite a while to really develop well. So there are three aspects really to the contribution of the platform to the signal. There is spectral noise. So if you have something that has a switching current in your electronics, then you have a spectral noise feature that largely can be filtered, just conventional data processing. But then there's the hard iron and soft iron effects that come from taking your whole platform. And by this, I mean, in this case, the person carrying the magnetometer with all the batteries, all the data acquisition, the edge computer, the ground truth GPS, the flux gate, all of that stuff has its own intrinsic magnetic field, and it has the variation in its magnetic field as you move around in different orientations in the field that you're measuring, the Earth's field. And what's been really important to do there is come up with robust ways of calibrating that orientational dependence in your whole signal out of the measurement that you make with the OPM. So what we've developed is a pre-calibration step. Before we start taking data, there is something, and it's the best analogy is the what they used to call swinging a ship. To get a magnetic compass to work on a steel ship, Kelvin invented the binnacle, which is the thing that, if you think of a compass sitting on a wheelhouse, it's that big thing with the metal balls. That was how William Thomson earned enough money to become Lord Kelvin in the first place. He invented that thing, but critically what he did was he invented a calibration process for taking the ship moored in this direction, swinging it around this way, that way, the other way, and doing that taking enough measurements to adjust the binnacle to take out the hard iron error from the ship. We do a similar thing with our magnetometer before we take data. We move the platform through its full range of motion, and we perform a fit to that data that allows us to back out the hard iron effect from the true signal.
Okay, thank you very much. So it seems that we do not have any additional questions. So at this point, I will take the chance to thank you so much for taking the time to discuss your work with us today. It was very much appreciated, and I find it very, very interesting. So I'm looking forward to hear more the next time.
Thank you very much. It's a real pleasure. So yeah, thank you for all your efforts organising the seminar series. It's great. Thank you.